Sounds like it's here.
Catherine.
Get some toys. No, you're not gonna toss egg, are you? Is it hard boiled?
It's not hard boiled. Not boiled at all.
Do I sound okay on Zoom? Is anyone confirmed or denied?
Guys,
Yeah, you sound fine.
you sound fine.
I don't know what's going on with this. I'm gonna try one more time to turn off the speaker.
Maybe try rejoining.
I will try that once and then.
Then we can keep going. I mean,
So let's leave meeting. Would you like to leave? Yes, you sucked. Okay. And of course try one more time. Do we have a hard stop? Like everyone has to go to class after this, or we're pretty good?
we're pretty good.
Join. I'm gonna say. Okay, now let's go share screen.
There you go. I can hear you here.
See, I'm not selecting share sound. All right, you know what? We're just gonna go with it. Minimize that. Okay, wonderful. Okay, let's get started. San Jose State. I'm so happy.
We're happy to have you too.
Thank you so much, Maria, for setting this up. Thanks everyone for showing up. I was just realizing this is my first time putting on a presentation on behalf of ADI since the stupid pandemic started. Really excited to be back, like in real life in person. Yeah, both my kids did online school for like a year and a half, and it was awful. It was exhausting. But anyway, my name is Mark Thoren. I am now a systems engineer at Analog Devices. Everyone's heard of Analog Devices? Everyone's heard of linear technology? Yeah, so linear tech, I joined linear tech in 2001. Who was not born in 2001? Okay, got it. Yeah, so okay, so I feel a little bit old, but not too bad. Yeah, so I worked for linear technology, and from the start, linear tech is known for power parts. I supported mixed signal. I was like the oddball in the odd corner of the company. That's things like analog to digital converters, digital to analog converters, and it's just been so much fun. Lots of things involving op amps and microcontrollers and FPGAs. Like the thing about data converters is you get a big system view of what your customers are building. Super interesting. And let's see, a couple of things about San Jose State. I was also telling Marielle here, when I first got out here, I was a little bit intimidated because I was like interviewing and working with people from like Stanford and MIT and Berkeley. The best engineers I've hired come from San Jose State. So you're in the right places. Great. Thank you, Dave, thank you, Dave, for producing so many hireable engineers there.
So talk to your lawmakers about the budget surplus in faculty.
Wait, is that a joke? There is a surplus?
That's estimated to be a 31 billion surplus.
Oh my God. Yeah, let's spend it on education. Okay. So this afternoon, we're going to talk about noise, filters, and mixed mode signal chains. And I actually gave a version of this presentation a number of years ago, and I kind of put it together just as a sort of a random topic. And it went over pretty well, but then I'm in front of like real professional engineers giving a talk on mixed mode signal chains. And I start talking about noise and noise density, and it was a 6-hour presentation, and people's eyes were glazing over. And I'm like, okay, who wants a refresher on noise? And everyone's hand went up. And so I pulled out my San Jose State presentation and went through it verbatim. And that went over really well. So I've been itching to redo some of this stuff and do some experiments. So let's continue on here. This is boring. Okay, so this is for my boss, and I'm going to come back later. I want Dave to take a picture of me in front of this so he knows I showed this here. So analog devices is a, oh, great. We'll get a picture here.
No, for promotional, you
Yeah,
know.
for promotional here. Okay, so analog devices makes chips that go in everything. The world cannot live without these devices. It's things that, forget about cell phones. It's infrastructure, it's measurement circuits. One of my favorite examples on some of the communication stuff is, you remember the cave rescue in Thailand? Those kids that got trapped in the cave? Well, how do you think they established a communication link through the cave? Like, you can't use regular walkie-talkies because as soon as you go around a corner, then that breaks. So what they did was they used digital radios with our chip in it, and they spread them down the cave like breadcrumbs, establish a mesh network, and now you've got communication line down this cave here. That stuff is freaking magic. Okay, power, instrumentation, airplanes, and all kinds of good stuff. We're a global company and a very old company. What's 2021 minus 1965? It's old. And headquartered in Massachusetts, 15,000 employees, probably more. This was taken prior to our Maxim merger. All over the world, we make a ton of parts, like op amps and RF components, you name it, we make it, except for FPGAs, memory, and processors, because there's no money in that. I could say that much more definitively with linear technology. We only made high-end analog that we could charge a lot of money for. So we would never touch memory or things like that are commoditized. Public company, obviously, and we're everywhere. So of course, we've got facilities out here that, I know one gentleman here was interviewing with analog devices. We're set up all around the world. Okay. So let's get into business here, and I promise I'm not going to read this whole thing here. But first, what's a signal, right? We're going to talk about signals and signal to noise ratio. So a signal, I kind of bolded the real definition we're going to use here. It's just a detectable physical quantity of some sort, like a voltage, that I use to communicate information. So I can send a signal down a wire. What else can I send down a wire? Data. Well, data is a signal, right? Or information, right? More generally, information. I can send information down a wire. What else? Power. Yeah, someone said power. Yeah, so power and information. So we're going to focus on information here. I've also got a little mean history here. Well, you can look it up afterward. Look up all your base are belong to us. We get signal was at the front of this thing. So Tony probably knows this. Okay, he knows it. Okay, one of the first memes here, but yeah, as I was putting this together, I'm like, oh yeah, we get signal. Okay. And then what is noise? Well, anyone into thrash metal? So Sound of White Noise, one of my favorite albums. Noise it's kind of like a signal, but it's one that you don't want. It's an interfering signal of some sort. And do you have a picture in your mind of what noise sounds like? Dave, yeah, static, exactly. Something like that. Okay, we'll get into some other examples before too long here. But the point is, it's an interfering signal. And let's just keep moving on here. So signal to noise ratio, why do we care here? Again, I'm not going to read this whole slide, obviously. I'll make these available afterwards. But noise, if you think about it, it limits, if you're measuring something, if you're measuring weight or voltage, does it limit your precision? Well, not really, because if I have a lot of time, if I have a noisy signal that I know is bouncing around the correct value from statistics, how do I make that reading better? I have noisy readings, how do I make them better? Average, right, averaging. And we're going to talk a lot about averaging here as well. So, but in order to average, I need lots of readings, so I need time, right? So I can get that information if I have enough time. If I don't have time, I better get rid of noise. I better make my signal quieter. And there's a famous paper, the foundation of this is the Shannon theorem. So Dave, when do we start studying Shannon?
Hmm.
Oh, okay, probably, maybe never.
I mean, no, it'd be mentioned in the EE 160.
116, okay.
But not everybody takes that.
Yep. Yeah, so,
And I'm thinking 102, it should be there as
okay.
well.
But yeah, beyond an intro course, this is like graduate PhD
Are we
level
gonna have
stuff.
quiz after your presentation?
Pardon?
Are we gonna have a quiz?
No. So my objective here is not to convey any real information
Okay.
aside from the spark of interest to look deeper into this. Because we have like an hour, so we have enough time to get excited. And then you do homework on your own. But yeah, so this paper, it's a famous paper, it's all over the internet here, and it really establishes that limit between bit error rate and signal to noise ratio. How much power does my cell phone need to get the signal across the room or to the next cell phone tower? That's all dictated by Shannon's theorem here. Okay, yeah, so speed, precision trade-off, and it limits information bandwidth. Okay, I promise we're gonna get to more pictures and some live demos here in a hurry. So who's seen this unit before? A nanovolt per root hertz. Tony's seen it. Anyone out here, don't be shy. What are op-amp specs that you know? What are some op-amp specs when you start using it? Pardon?
Price.
Price, okay, that's a good one, right? If you pay more, you hope to get a better performance op-amp. But what does that mean? It means more of something and less of something. Offset,
Offset
right?
voltage.
So we've got offset. We've got bias current, right? My inputs have a little bit of current. I've got bandwidth, right? So I might have a slow amplifier or a fast amplifier. And every amplifier also corrupts the signal in some way. It adds noise. If I play an audio signal through that amplifier, it's going to add some noise. And you'll see these graphs here that show what that noise level is. And what's the audio frequency range? Like, what's the human ear sensitive to? 200? A little bit lower. So, okay, so subwoofer in your car, 20 hertz or maybe a little bit lower. 20 kilohertz for a young kid whose ears haven't been destroyed by those subwoofers. Yeah, so about 20 hertz to 20 kilohertz. So I've got a couple of op amps shown here. And just qualitatively, this is the noise level that this op amp produces. And if I'm looking at audio, that's like 20 hertz, 100. So somewhere out here is 20 kilohertz. So right in here, my op amps, both of these op amps are generating some noise. One is clearly better. It's lower noise. Like, how do I quantify that? Here, I've got a little peak. Right? And this is in frequency domain, right? We've all seen FFT plots, time domain plots, and frequency domain plots. So a pure tone, like a 100 hertz sine wave, is an impulse right here. And a 1 kilohertz sine wave is an impulse here. But what the heck is this? How can I have continuous frequency? Like, what is that? What does that sound like? This looks kind of like a tone, but this just means that I've got more up at this high frequency, but it's at a megahertz. Does my ear care? Yeah, so my ear doesn't care about a megahertz. If I'm taking very precise voltage measurements, notice at low frequency, I've got more wiggle. So this is called a 1/f corner, and that's a property of most op amps that don't correct for it in some way. So these op amps, they have, I think of it as personalities. Every op amp has its own personality, and this is one of them. But what the heck is this continuous distribution here? Let's look at those units. Nanovolt per root hertz, and we'll focus on voltage, but there's also current noise, picovolts per root hertz. So what that sort of means is, you can kind of think of it, if I have a wider bandwidth, I have a larger number in the numerator, I'm sorry, per root hertz. If I multiply by a wider bandwidth, I have more noise. So let's start thinking in those terms. More bandwidth, more noise. Kind of makes sense, right? Let's dig a little deeper. Oops. So a nanovolt per root hertz. If you look a little deeper into your textbook, you'll find a formula for the noise of a resistor. So have we seen that concept before, that resistors have some noise that they produce, right? A couple of nods here. So we all know that a resistor, maybe we haven't like measured it ourselves yet, but we have some sense that a resistor produces noise. And here's that formula. It's 4 times Boltzmann's constant times absolute temperature times the resistance. And if I run through that calculation with a 1 meg ohm resistor, I get 130 nanovolts per root hertz. So forget the absolute number, but just know that it's 130 nanovolts per root hertz. So I always like to go back to fundamentals, right? A resistor, you can hold it in your hand, but let's go back and try to break this thing apart into really easy pieces. What if I had a whole bunch of signal generators? Who's used a signal generator, right? Everyone's used a signal generator. So I'm going to take all the signal generators on all these benches, and I'm going to set this guy to 100 hertz, that guy to 101, 102, 103. I'm going to turn their amplitudes to 130 nanovolts. So small voltage, but just you get the concept. Then I'm going to add them all together. Well, shoot, if I have a 1 hertz filter, I get 130 nanovolts, right? If I set that filter center frequency to 102 hertz, I get 130 nanovolts. So I'm starting to build up this idea of a density. I've got lots of tones at different frequencies. And if I increase my bandwidth, I sum more of them together and my noise gets bigger. Who's used LT Spice? Okay, thanks, Dave. You're awesome. Okay, so LT Spice is, of course, a circuit simulator. And so let's try to get some idea of how those signals add, right? Because if I add 130 nanovolts here to 130 nanovolts, do I get 260 nanovolts out? Or do I get some other number? Okay, and it turns out you don't. It turns out that unrelated tones, if I have frequencies that are all spread apart and they're not related, the voltages don't add, the powers add. And so this is a really super duper simple signal and noise source. And we're going to try and see if LT Spice agrees with that. So we're going to take our signal, our 10 volt signal, and we're going to put it across a 1 ohm resistor here. So I'm going to measure the power that signal is delivering into 1 ohm. Then I'm going to look at the power that my noise signal delivers into 1 ohm. And then I'm going to look at the sum of those two. So I've got power noise, I've got power signal, and I've got power total. All of these are up on GitHub, by the way. So we'll put these up here. And sure enough, if I do that, if I run, you've seen this in LT Spice, right? I can run a graph here. If I do that, I see that my RMS voltage of that first source is 10 volts, 10 volts. And if I look at the power in that resistor, it's 100 watts. And if I look at the power of my total, yeah, so I've got 100 watts in that first resistor. I've got 1 watt in that second resistor. Yeah, I've got, what do I have here? I've got 1 volt RMS and 10 volts RMS, right? So 1 and 10, but so my voltages don't add. I don't get 11 volts out. I get root sum square. So square both numbers, add them, take the square root. And this sort of shows that my total power in that resistor is 101 watts. Okay, so that's a fundamental concept here. As I keep adding these noises together, I don't add them directly. I square them, sum them, take the square root. And I have a little note here that the proof is in Parsifal's theorem. That sent me down a YouTube wormhole one night. So there's all kinds of great proofs of Parsifal's theorem on various YouTube math channels and all that. Okay, so we're going to get to some demos here in a second here. So tools for generating signals and noise. So we're going to generate a couple of signals and noises here in a second here. Benchtop arbitrary waveform generator. I see some back there. Dave is a big cheerleader for this little guy here. Have these students used these? You guys
Yep.
use the
Sure, I mean, if they were San Jose State students last year, yeah.
Okay,
That
yeah,
was a
fantastic.
de facto thing.
We use these inside as well. We use them for testing ICs just because they're so cheap and so easy to use. And if you break it, you don't have to be too upset about it. Okay, so this is the software associated with that. It turns out that Scopy can also generate some noise. Has anyone used the new radio? Does that ring a bell? So the new radio is a toy for playing with software-defined radio applications, and that has a bunch of cool signal sources as well. This is running on my Raspberry Pi, and I play those tones out the sound card of the Raspberry Pi. So it's a really neat little toy. And then in simulation, everyone uses Python.
I've used it.
Pardon?
Yeah, I've used it.
Yeah, so Python is like my sledgehammer. I use it for everything, and we'll get to that in a second as well. Okay, so some tools for generating both simulation and in real life, and for Python, it's both. I took a little picture here of this little noise source. So noise is important, and if you don't believe that, this is a little tiny box about that big, and it costs $19,000. So that's a heck of an expensive little noise source. So that's how important it is to characterize and understand the properties of noise and how your system reacts to it. Okay, demo time. Like I said, Python is my sledgehammer. Dave, have you shown these guys how to use libm2k? It's super easy to talk to this thing in Python. So let's go ahead and do it. So what we're going to do is generate a signal. And we're going to do that by setting up a sample rate of 7,500 samples per second. That's for my output. I'm going to read back some samples here. And then really simple math. I've used NumPy before. Okay, great. So NumPy, really easy to use number crunching library here. So I'm using NumPy's linspace functions and the sine function. My signal power, 1.414, right? So I get 1 volt RMS. And then I'm going to call it, carrier. And then to push it to my M2K, all I do is A out that push and I stick my variable in there. And let's see what happens. So we'll go to my favorite editor here, and I think I am good to go. Oh, go over here. This is getting in the way a little bit. Oh, spoiler alert.
Oh,
Oops. Okay, so it turns out that was actually noise fs discrete tones equals true. Let's see, noise. Yes, you can see I've got a bunch of stuff set up here. So I'm going to set my noise power equal to 0. Okay, modulate equals false. Okay, and now let's try again. Oh, didn't like that. Noise power equals 0. Oh. Okay, so everyone can hear that? Okay, good. I picked a frequency, that's not too terribly high. So that's the 1 kilohertz. We'll call it a signal. I call it carrier here because it's a signal that we're going to modulate. We're going to put some information on top of it. Okay, so let's stop this guy here. Okay, and I've actually got a plot up here that we'll take down. Next, we are going to generate some noise. And so I'm going to say noise power equals 707. This signal power, oops, equals 0. Oh, that was my noise again. Oh. Okay, what happened? Noise Fs? Oh, here. Comment out that one here. That was a spoiler. That sounded an awful lot like noise. But this, yeah, so we can hear that. Okay, sounds kind of like the signal, right? It's a sine wave. But if it's not the signal I'm looking for, then it's noise. Okay, Okay, now let's add a message to our signal. And let's see, so we're gonna go signal power. We're gonna bring that back up again. And let's just call our noise power 0. And let's add a message.
That was a Morse code type thing. The
You
first
gave
time
away
you
the
read.
answer. Okay. Yeah. So, okay, all right. So we can hear that message, right? What does that mean? SOS, right? Help. So pretty important message there. And there's a reason I chose that, right? It used to be that in order to get a ham radio license, you had to know Morse code. And that's why. And the reason why Morse code is so useful is because it has very low bandwidth. You can take a very low power transmitter, transmit Morse code, and someone with the right radio can filter out all the noise and pick up that information. So it's not a lot of information, but if you're a ship out in the middle of the ocean, pretty important information. Okay, so let's go back and start adding in our interferers. And let's notice something here. So if I'm setting my signal power, this is actually 0.5 volt RMS, so it's not too loud. If my signal power is a volt RMS or 0.5 volt RMS, and my noise power is the same, what's my signal to noise ratio in decibels? Zero.
That's in power, okay.
Yeah, 0. So this is a 0 dB SNR. Sounds really bad, right? Signal is the same as my noise. If you were listening to headphones, that would be really staticky AM. Okay, but let's see if we can still pick out the message with our ears. Still hear the message? Okay, yeah. So even though our noise power is the same, it's in the band of our ears, our brains can still pick that out. Okay, so 0 dB SNR is not necessarily a bad thing if I'm not trying to squeeze a lot of information through. If I was trying to squeeze through a JPEG or a cat video, I couldn't do it because I've, at least not very fast, because I've got so much extra noise. Now we had that idea of a noise as a whole bunch of tones. Let's start digging into that a little bit. And by the way, here is the, let's blow this up a little bit. So I'm actually capturing back the voltage waveforms on both of these. So spoiler alert, the blue is that noisy signal here. If I look at, this is my message, my Morse code signal here, and you can actually see the sidebands in my captured back signal, right? So pure tone is straight up and down. As soon as I put any information on that tone, it spreads out. I get these little sidebands out here. And here's my noise tone over here. Okay, so let's kill this one here. Now what we're going to do is we're going to, instead of my noise being a single tone, let's bring this up to the top a little bit here. So the way this program is set up, if I can do this, is I can define what I want for my noise. I can have a 1500 hertz tone, or I can make a whole bunch of tones. And if I make a whole bunch of tones, I divide it by the square root of my vector here. So if I have 2 tones, I divide by square root of 2. 3 tones, divide by square root of 3. And we'll see why in a second there as well. Actually, we can do it down here. Let's see. This is kind of annoying. Okay. Signal carrier. Okay, you see this here? So another favorite NumPy function is the standard deviation. Standard deviation of a signal is its power level. It's directly related to how hot a resistor will get if I play that signal into the resistor. So standard deviation of my carrier is 0.5 volt. If I look at standard deviation of my noise, let's see. N-O-I-S-E. Okay, look at that. So I have two tones, half a volt, half a volt. Now let's break that noise into two tones. And we'll do that by, for the sake of completeness, we'll comment this out. Let's make that four tones. So I've taken my noise, and now instead of a single tone, I'm going to make four tones. So let's see what that sounds like. How are we doing on time here? Oh, we're doing great. So we've split our noise power out. Can we still get the message? Okay, and then let's go. Oops, that's not what I want to do. Okay, and then let's look at the plot here. And we're going to leave this up so we can flip back and forth. Oh, there it goes. Well, that's kind of a funky interference pattern here. But once again, you see, here's my signal. The reason the signal is lower is because I'm modulating it. It's not on all the time, so the FFT shows a lower amplitude. But my noise tones are a little bit different. They're roughly the same height over here. And the reason is my speaker's resonant. It doesn't have a perfectly flat response to it. Okay, but we're starting to break our noise apart. So now let's go, and instead of four tones, see where we're going with this here. Let's go to 25 tones. Okay, so all those numbers there, 100 hertz, 200, 300, 400, 500 hertz, dividing by some number to keep the power level, the net power level, the same. So still 0 dB SNR. Okay, and let's see what the plot looks like here. Oh, that's pretty trippy here, right? So we've taken these four tones and we're spreading it out here, right? We can still distinguish these tones. Do you think we'll always be able to distinguish them if we keep doing this? Yeah, so eventually, let's keep going and going and going here. So now, instead of using that vector of tones, let's go and we're going to use numpy.linspace. So that just gives me a whole bunch of numbers from point A to point B. All right, and we're going to give it 250 tones now. Still hear the message? I hear a weird pattern, like a silent. Yeah, I hear a beat frequency. And I sort of tried.
It's
So
not repeating, is it?
it's not repeating. I think it's because my tones are not 100% unrelated. And if we look at, so I tried to pull some tricks in here. And so much fun playing with all these signals and noises and stuff. So when I added all those noises together, I created a delta frequency. So I tried to wiggle the tones around a little bit so that they're not all related. And then I also add a random phase. So all those sine waves, if I didn't randomize the phase, what do you think you'd get? What's a signal that has a flat frequency distribution where every tone has the same phase? Keep that in the back of your mind. We'll see it in a spice in a minute. Okay, we're going to do one more experiment here. We did 1,000 tones here. Now, a couple months back, I submitted a paper to the Scientific Python conference, SciPy conference. And as part of that, I built up a little frequency that fills out all of the tones in a given data set. So you're familiar with the FFT, right? Fourier transform. So Fourier transform takes a time signal and decomposes it into frequency. So what about going the other way? Just the same operation with some scaling constants there. So what this function does is if I give it a whole bunch of ones, if I give it a flat frequency distribution and I say, hey, give me time points, it spits out noise that I can play back through this signal generator here. And we'll flip back to PowerPoint a little bit for a second. Alrighty here. So again, just an illustration of these same concepts here: modulation, split the tone, 24 tones, and finally 250 tones. Okay. I won't dwell on this. Let's just see what it sounds like. Okay, so we're going to do one more thing here. We're going to discrete tones equals false. Okay, and I think that ought to do it. So that is that much more pure. So yeah, what's the big deal about making noise? If you do it well enough, you can charge $18,000 for a little box that generates it. Okay, great.
In doing that summer project I showed you,
Yes. Yep.
we've used noise to detect the signal.
Yes. Yep.
Getting the
super-
noise to work took most of the time.
Yep. Yeah. Super
that,
duper useful to get a high quality noise source for testing things out and really understanding how they respond. Super duper valuable. Okay, and here's my function to do this. It's up on GitHub. We'll put a link out there. Okay, so back to LT Spice for a minute. We've seen this before. I can take LT Spice. I can measure the power that goes into resistors if I want to add noises together. So again, this is another little science experiment I did a while back. And I kind of went crazy with voltage sources in LT Spice, and Catherine's laughing because she knows how ludicrous this is. But yeah, I wanted to try here. If I take 36 noise sources all set to 1 volt RMS, do I get 36 volts out here? No, I get 6 volts RMS. So again, just an illustration of that. And I asked a question back there: what if I don't randomize those phases? What do I get out of it? What does that look like? Okay, so I took this simulation.
Maybe if you said, if you had the Laplace.
Yeah.
And there was no frequency deviation, it's
Yep.
just constant. What's the inverse Laplace of that?
What do you think? Anyone remember? So if I have a continuous frequency distribution, we know that random noise, we know that that has that property. What's another signal that has all frequencies? What's that? So a square wave doesn't have all frequencies. A square wave has F, 3F, 5F, 7F. It has odd harmonics. A spike, yeah, so an impulse function, right? So remember back from signals and systems, a single impulse happening at time 0 has all frequencies from the Big Bang to the Big Crunch. Of course, we don't have that in real life. We don't have perfect impulses. We have close to perfect impulses. And that's sort of what we're seeing here. I've got lots and lots of frequencies, and I haven't adjusted their phase. They're all sine waves. They all start at 0 and they peak at some point in the future. And if you add those together, well, if I had infinity of those, then I would get an impulse train. Except I don't have infinity of those. I have 36. And so what is this function? Sync, exactly. So it turns out if it repeats, it's a sum of cosines, but the more and more of these you have, it approaches a synchy function. So the first time I ran this, oh my gosh, what do we have to do here? Well, the answer is I go and Monte Carlo the phases. So in LT Spice, another super useful LT Spice trick is Monte Carlo. So that lets you randomize basically any parameter. And in this case, I randomize the phase. That's starting to look like noise. Okay, and then if I take the FFT in LT Spice, here's DC, here's some frequency. This sort of looks like a flat frequency distribution. I can still distinguish my tones because they're not spaced out very far, but it's starting to look like a flat distribution. And then if I window the thing a little bit, and if I screw with my frequencies a little bit, now LT Spice can't distinguish anymore. Now it's starting to look more and more like a continuous distribution. And so that's, if there's anything I'd like you to take out of it, it's this idea that you can sort of think of this continuous noise as a bunch of discrete tones that are so close that you can't tell one from the next. And you can do that in LT Spice or Python, etc. Okay, so I said in the premise here that we're going to talk about noise. We think we have a better understanding of noise. If you go home, you think you can make one using your sound card or your M2K. If anyone hasn't played with libm2k, this Python library, it is a freaking blast. It's like 5 lines of code to make any signal you want. Reverse is true too. You can grab signals and analyze them and all that stuff. So if you don't like Scopy, then write your own instrument. Okay, so how do I?
No, I like Scopy.
So Scopy's great. Scopy's great, but if you wanted to do something that it doesn't do, it's a little Python program, which is pretty wild. Okay, so we talked about noise. How do we get rid of noise? It's kind of written up here. It's you filter out the noise. And if we go back, I'm going to go back a bunch of slides here to the beginning. Okay, here. So I have a system where my signal of interest is here. My A to D converter bandwidth goes all the way over here. And this noise mountain is a problem. It's close enough to my signal that I want to get rid of it. And I get rid of it with a filter. And then so we've already got the idea in our head. We've got the idea in our head that as we increase our noise bandwidth, our total noise increases, this interfering noise. Well, how much noise? How much noise? This is the formula for what's called equivalent noise bandwidth. It says, if I take infinite noise from DC to daylight and I blast it at my filter, how much noise actually gets through? That little gold box earlier, that goes out to 60 gigahertz. So if I take a little, like a 1 hertz filter and I blast it with 60 gigahertz noise, what do you think is going to come out of it? Is it going to be really, really high because it's such a high noise frequency, or is there some limitation there? And so here's the magic formula that tells you how to do that. It says, if I have some filter with a responsive AB, we won't go through the deep math here, but if we integrate from 0 frequency to infinite frequency, we square the frequency and then divide it by, we square, integrate, and then divide by its amplitude squared. We get this magic number, this equivalent noise bandwidth. So to drive this home, let's just look at a really simple example. And by the way, you don't need a very complicated filter in that formula where you just scream uncle and go straight to some online equation solver, which is exactly what I did. So here's my favorite example. It's a 1 hertz filter. So very low frequency filter. And I can build one of those with a 15K resistor and a 10 microfarad capacitor. And I am going to blast the heck out of this with noise from low frequency from DC out to 60 gigahertz and beyond, just infinite noise blasting at this thing. How much noise comes out? And the answer is it's whatever that noise density is times pi over 2. So this 1 hertz filter, as far as broadband noise is concerned, it only lets through 1.5 hertz worth of noise. So it doesn't matter that my noise goes out to daylight to gigahertz and beyond. This does a pretty darn good job. So it sounds like a pretty good deal for such a simple filter, doesn't it? So even simple filters are pardon? Oh, I thought someone said something. Yeah, so even though very simple filters can be effective when they're used properly. Okay, how do we talked about this earlier. How do I reduce noise in the digital domain? If I'm collecting samples and they're noisy, then how do I get rid of that noise? And one way is by averaging. So here's my favorite example is you hear in the financial news about like the 12-month running average or the 3-week running average or something like that. Well, that 12-month running average is a digital filter. It's a digital filter with 12 taps, 12 months. I multiply it by some noisy economic data here, and that reduces my noise level. Mathematically, what I'm doing is I'm taking a bunch of ones. You know a NumPy function to generate ones? NumPy dot ones. So this is like NumPy dot ones with a 12 in it, and I multiply that by my data. Every time I multiply, I sum them together, divide by 12, and I produce a data point. I slide this and do it again, slide it and do it again. That's a digital filter. And you see it has a rectangular response, 0, 0, 0, 1 for 12 samples, and then down. So it's a boxcar in time and a sync in frequency. So let's play with this a little bit. What FCOJ stands for, Dave knows. Frozen concentrated orange juice. It's the most boring.
Right now I know
economic
the
data.
movie.
Yeah.
I know the movie.
An example of that. So you probably haven't studied data converters, a dual slope converter. Yeah, so the multimeter that you have, the benchtop meters back there are probably of a dual slope type. So I won't dive into this too deep, but this is an electrical circuit that does a running average effectively. So again, it's a circuit that has a rectangular response in the time domain and sync in the frequency domain. Okay, so here's that pictorially. If I have a circuit that is sensitive for some time period, like 200 milliseconds, this is its frequency domain response, right? So I have 1 over 200 milliseconds is 5 hertz. Any stuff that's happening at 5 hertz is in that null. Any stuff that's happening at 10 is in this null. And I have this sync response out here as well. So let's ask that same question. I'm going to blast this filter with infinite noise from DC to daylight. Right, so I have my little handheld multimeter and I'm blasting it with noise. How much noise actually gets through? Who wants to integrate the sync function squared from 0 to infinity? Yeah,
No,
me neither. Okay, so I head over to Symbolab here, and sure enough, it gives me a solid answer. So if I integrate sine pi x over pi x squared by dx and take it from 0 to infinity, the answer is 1/2. Right? That's a pretty easy number. So that says if I blast the heck out of this filter from DC to daylight, I get 2.5 hertz worth of noise out of it. Okay, so again, very simple filter, but very effective when applied properly. Okay, so let's see. And then I also said in my title here that we're going to talk about mixed mode signal chains. And so I think we're going to end a little bit, not too much after this here, but here's sort of an example of a mixed mode signal chain that ties some of these ideas together. And then I think we'll leave it to self-study after this. So what do I do with a mixed mode signal chain? I have some sensor, maybe it's a blood pressure sensor or a strain sensor or a weigh scale or something like that. And I have a resistor, which also produces noise. And you always have some resistance. Every sensor has some fundamental limitation to it. I may have an amplifier. And we saw in that first slide that every single amplifier has its own noise personality. I may take that amplifier and I might want to get rid of some of its noise with this low pass filter here. And then finally, I digitize. And after I'm in the digital domain, I can average those values out over and over again, and I can further drop my noise down. And so again, this is a very simple representation of a mixed mode signal chain, and it's represented, kind of everywhere. This is your cell phone, where you have a microphone, analog signal conditioning, D to A converter that's in some little SoC buried in your phone. Then I enter the digital domain. Maybe I translate this to MP3 before sending it over the airwaves or something like that. And then, oh boy, this is going to get complicated in a hurry. Questions so far? We've covered a lot and we've talked really fast, or I've talked really fast. Questions so far? Who's totally lost? Totally lost. Okay. Who wants to do a little more study? Like if we put this up as a wiki exercise and play around with some of this stuff. Yeah, so super interesting. I mean, how cool is it to be able to define a bunch of tones with a simple little program, play it out my M2K and listen to it on the speaker. So that's really how you build intuition on these things. Most people I interview.
I'm sorry, I have to go.
Oh, Dave, thank you so much.
No, this is great.
Okay.
Yeah.
could show up on a 110 final review.
Good thing I'm done with that.
All right.
Lab manual will be
Lab
updated
manual.
next
I'm going to
semester.
see what else we have here. Thank you so much, Dave. Okay.
Thanks, Dave.
About most people you interview,
Pardon?
you're saying something about most of the people that you.
Yeah, most of the people I interview don't have a solid understanding of noise. They don't have a solid understanding of, like, you measure stuff in electrical engineering all the time. I measure this, I get a number out. Like, how perfect is it? How close are you to some fundamental limit that I can't get beyond? Yes, Tony.
When you are about interviewing, when you are interviewing, how important is it how the candidate conveys their understanding? How do you prefer that they convey it? For example, for like equations, schematics, or just talking in English words?
That is an excellent question. I do my interview seat of the pants. So I'll tell you my personal philosophy. I like an interview candidate that can talk a lot, that can talk through their thought process. I almost don't care that someone knows a theoretical something or other or knows equations off the top of their head. I like to use a lot of op-amp questions that don't fit standard equations, like to force people to think their way through it. It's like, oh, this isn't RF over RN. How can I solve this equation, right? And Catherine's interviewed people and probably used the same questions here. Talk me through, yeah, talk the interviewer through your thought process. If you don't know, admit it. Say, I need one more piece of information. I don't know how to get it, but if I could, then I can walk a little bit further through this thing. I don't have a picture of it here, but I have the world's stupidest boost converter that uses a variable capacitor and a 9-volt battery. You know what I'm talking about here. Yeah, exactly. And it's like a physics experiment, right? You look at this thing and it looks like this crazy contraption. And if you say, hey, you've seen this in your physics book before, this is a capacitor, and I'm going to charge it to some voltage, and I'm going to pull the plates apart and all that. So I like to ask a lot of sort of weird questions, not to be mean, but to sort of probe. It's like, hey, did you really understand what you learned in your physics class or your mechanical engineering class or something like that? And and I've already let my secret out of the bag, the backpack test. Build stuff, understand it. And it doesn't have to be physical stuff. Send your GitHub repository, right? If you're doing coding, if you're mostly a code weenie, put your stuff up on GitHub. Make it publicly visible. If there's a GitHub link on a resume, you better believe I've hunted through every single piece of code in that repository.
Don't look at my code.
Don't look at mine either. Okay, I think I'm going to leave it off here. Questions, comments? What should we talk about next if we do this again? Yeah, go ahead.
Did you expect an actual candidate to with a lot of big signal stuff?
I'd like to see the interest, because you've got 4 years to study. You're drinking from a fire hose, right? So you don't have a chance to dig really, really deep into stuff. And I'll tell you I recently had some interview candidates, they're actually in the Philippines, and 2 candidates, one was a lot more personable and sort of more outgoing. Couldn't really tell me, like, no indication that he'd asked the questions about how do I go deeper into this proximity sensor. He was doing some parking sensor. How did you connect this to your Arduino? Oh, I just wired it up and used the library. Well, like, what signal went over that wire between your sensor and the Arduino? Was it asynchronous serial? Was it I2C? Was it SPI? Right? No, I just bought the shield and the library just magically worked. Well, why did it work? Like, what? Dig deeper, dig deeper. So that's what I'd be looking for is, when you see something like that, you can't be perfect at everything, but the thing that interests you, have you dug all the way down? Do you know, for me, I'm a history nerd. I love studying electronic history. Who's been to Computer History Museum? Yeah, go if you haven't been. It's freaking amazing to understand that thought process. And even in mixed signal, I make a statement here that sampling faster is better. Why is that? It's because you know about aliasing. If I sample faster, aliasing is less of a concern. Filtering in the digital domain used to be a pain in the butt and super expensive. It's not anymore. Now it's more expensive to buy a bunch of op amps and matched components and all that stuff. So over time, these ideas have shifted. So, study that history. Can you explain to me how that multimeter works, that old multimeter works? And it doesn't have to be a multimeter. Like, what's your interest? Cars, there you go. So, even there, carburetors to fuel injection. Like what do the control systems look like? There's a million different subsystems in cars. Electric cars, what's the efficiency of a gas engine versus an electric motor? Like fundamental questions like that. So again, that's just random, just a few random thoughts on that. Pizza's getting cold. Okay, all right, thank you so much. Very attentive here. Yeah. Stop share. And everyone on Zoom, thank you so much.